Hey everybody, this is the last class U video. U is in the letter, not YOU. And before we get going, I just wanted to remind you of a few business things for the last few days of the class. So most of you have turned in homework RS, that's great. For those of you that haven't, please do so. After you turn in homework RS, I recommend doing the following 4 things in order. First, take quiz 4, because it doesn't have any of the material from homework TU. Second, watch this video. So if you haven't taken quiz 4, you should, you could watch this video first, but you can totally take quiz 4 before watching this lesson. Third, do homework T/U. And finally, take the final. And the final will be available Sunday morning at 6 a.m. If you have any issues accessing it, you are always welcome to email me. As far as the final goes, just taking a quick look at it, I would say when you take the final, don't ignore the front page, but like the front page has like the exam is due at 5 p.m. on Friday, September 11th. That's not the right due date. I used an old test. The exam is due Thursday at 11 p.m. I think. So do try and finish it by Thursday. If you run into issues, let me know. Work it out. As far as the content of the final, I'm just looking at it here. There is trigonometry, finding sine, cosine, tangent, secant, cosecant, cotangent of the usual angle values. There's some half angle formula stuff. There's some angle sum stuff. There's some graphing some trig functions. There's solving some trig equations. There's finding an inverse trig. There's 1 or 2 questions where I ask you to find a logarithmic value. We'll talk about how to do that today. There's solving some equations like with factoring by grouping or finding a greatest common factor. There is also some U substitution problems. You don't have to do a U sub, but you can. There's graphing some lines, some parabolas, some polynomials, graphing an exponential or 2, and graphing a couple logarithms. And there's some extra credit with creating a polynomial graph. So yeah, it's not too much. It may look long. It's not so long. Do your best. I don't remember what the time limit is for it, but it should say what the time limit is on Gradescope. So once you start, try to finish it within that time limit. If for some reason you run into an issue, you're welcome to email me the exam. Try not to go too much longer over. But yeah. All right, I think that's all the business stuff to get out of the way. Let's go ahead and talk about class U. So let me go ahead and share my screen here. So hopefully you can see that, class U, logarithms, and how to graph them. So like we talked about a few weeks ago, when I think of logarithms, I'm really thinking of this relationship, that 2 to the 3rd equals 8 is equivalent to log base 2 of 8 equal to 3. And when I read this, right, the words I say when I read the statement is, this is the exponent, right, because the logarithm is an exponent, right? The logarithm is equal to the exponent there, to which we raise 2, right? We're raising 2 to that power, or to that exponent, to get 8. Those are the words I'm thinking. And then we can say, since we know that 2 raised to the 3rd power equals 8, then we get that log base 2 of 8 is equal to 3. And then we could extend this to a few more examples. For example, what about log base 3 of 81? Well, we know that log base 3 of 81 is an exponent. It's the exponent. You don't have to write these words out, but I'm going to write them. It's the exponent to which we raise 3 to get 81. So we know, or we've seen at least, that 3 raised to the 4th power equals 81. That means that log base 3 of 81 must equal 4. So that's kind of the whole deal. Let's do a few more things with this, though. Let me put my papers over. I will also scan and upload these notes, as I usually do. So just another couple quick more examples, because I want you all to be super cool with this. What's log base 5 of 25? Be careful. Some people say it's 5. It's not. 5 times 5 is 25. But 5 squared is equal to 25. So right, we're looking for the power, not what you multiply it by. So log base 5 of 25 equals 2 because 5 to the second power is equal to 25. Or log base, let's look at some other interesting things. Log base 8 of 2, that's kind of a backwards one, equals 1/3 because 8 raised to the 1/3, which is the cube root of 8, is just 2. What else? I just wanted to give you guys a couple more interesting examples because it's kind of fun. Log base 4 of 1/16 is going to be -2 because 4 raised to the negative second power is equal to 1/4 squared, which is indeed 1/16. Right, so every time we are looking for the exponent. And in general, again, I'm just going to remind you again of my favorite one. I always remember this one. Log base 2 of 8 equals 3 because 2 to the third equals 8. And then very, very generally, we say that if y is equal to b to the x, that's equivalent to log base b of y equal to x. Right? And often when I'm looking at this logarithmic equation, I'm thinking, oh, b raised to this power equals that. Whoops, equals, not equals, equals. Okay. Yeah. I would remind you, or maybe not remind you, but I would kind of encourage you to think about the fact that this is exactly like how inverse trig functions look. When we talked about inverse trig functions, we were looking for a function that kind of undid what another function did or inverted the relationship of another function. So I'm going to call back to that for just a minute here. Throw my papers on the floor willy-nilly. So let's say the following. This is just like how the inverse trig functions work. I will say it's actually a little bit easier than inverse trig functions because inverse trig functions have some weird domain restrictions, whereas logarithmic and exponential functions don't have any weird domain restrictions. So, for example, I'll remind you that sine of pi over 6 is equal to 1/2, and that's equivalent to saying inverse sine of 1/2 equals pi over 6. Because inverse sine of 1/2, when you find inverse sine of 1/2, you're looking for the angle, that's pi over 6, that we take sine of to get, that's one word, to get 1/2. Sorry, I know that's terrible. Or the angle whose sine is equal to 1/2. In a similar way, I would say that inverse, or I should say cosine of pi over 4 equals, let's go 3 pi over 4 just to be fun. Cosine of 3 pi over 4 equals -√2/2 is equivalent to inverse cosine of -√2/2 equal to 3 pi over 4. And again, when we're finding the inverse cosine of -√2/2, we're saying we want the angle that if we take cosine of that angle, we get -√2/2. Well, of course, that angle is 3 pi over 4, because cosine of 3 pi over 4 is -√2/2. In the same sort of way, that's what we're doing with exponents and logarithms, right? We can say, we know that 5 cubed equals 125, and, or equivalently, log base 5 of 125 is equal to 3. Log base 5 of 125 is the exponent, or you can use the word power, either way. The exponent that we raise 5 to get 125. Oh, that exponent is 3. 5 to the third power equals 125. So that's kind of it. Let me just say one more thing again. So once again, I'm gonna write this like on one big page. It's kind of we have the log. Wow, it's a big log. Okay, log base b of y equal to x is equivalent to, well, again, I'm thinking of b raised to the x power is equal to y. So b raised to the x equals y. Or if you prefer, we can write it as y equal to b to the x, right? It doesn't matter which order we write the equation in. And again, right, b raised to the x equals y. So when I look at a logarithm, right, if someone says, hey, James, log base 4 of 64 equals 3, I'm gonna be like, well, yeah, that makes sense because 4 raised to the third power equals 64. Oh yeah, 4 cubed equals 64. That checks out. So hopefully that helps you understand how logarithms work a little bit better. The other thing we're going to do with them is we're going to graph them. And we are going to really kind of utilize the fact that logarithms have the inverse relationship that exponential functions have. So we're going to take our exponential functions and we're just going to graph the logarithms by inverting the x and y relationship. Here's what I mean. So let's go back to my favorite exponential graph, y equal to 2 to the x. We graphed this one last time, and we did it kind of nicely by plotting some points. So I'm going to plot some points again. Yeah, let's make a table here. So I've got my x values and my y values. And I'm going to pick some usual x values, 0, 1, 2, and 3, and -1, -2, and -3. And we know that 2 to the third is 8, and 2 squared is 4, and 2 to the first is just 2, and 2 to the 0 is 1, and 2 to the -1 is 1/2, and I'm getting kind of off here. 2 to the -2 is 1 over 2 squared, which is 1/4, and 2 to the -3rd is 1 over 2 cubed, which is 1 over 8. So graphing this, and hopefully I do a good job of graphing it right now. Let's see. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, no, just up to 8. I mean, you can go higher, but yeah. So, and then 1, 2, 3, and -1, -2, -3. And so when I plot this, I get the point 0, 1, 1, 2, 2, 4, 3, 8. And then I get -1, 1/2, -1, -2, 1/4, -3, 1/8. And we never get down, to, whoops, come on. Yeah, okay, you can do it. Gotta make the graphing noises. All right, yeah, there we go. That looks decent enough. Sure. You can label the points if you want. Actually, I'm going to label them here. So I've got the point 3, 8, and 2, 4, and 1, 2, and 0, 1, and -1/2, sorry, yeah, that's right. Sorry, no, -1, apologies, 1/2. Whoops, that's terrible. You could edit that out later. No, not really. And then that point there is -2, 1/4, and then that point there is -3, 1/8. Okay, so now what we're going to see is that the logarithmic graph has the exact same points, except x and y are all interchanged. So if I'm going to graph y equal to log base 2 of x, if I want to make a little table, I'm going to get the opposite values. I should say the inverse values. So I'm going to have x and y. So instead of having x be 3 and y be 8, I'm going to have x be 8, and log base 2 of 8 is 3, right? Because 2 to the third equals 8. And if x is 4, I'm going to pick the nice values of x. Log base 2 of 4 is 2. And if x is 2, log base 2 of 2 is 1. If x is 1, log base 2 of 1 is 0, because 2 to the 0 equals 1. In fact, fun fact, which I'll write this down on the next page in a minute, but log base anything of 1 is always going to equal 0. As long as the base is, well, we'll talk about the bases in a minute here because there's some restrictions on the bases, just like before. And then we could have a value of like 1/2. Log base 2 of 1/2 is -1, because 2 to the -1 is 1/2. And we could take the log base 2 of 1/4. And log base 2, I know my 2's are looking kind of sketchy there. Log base 2 of 1/4 is -2, because 2 to the -2 equals 1/4. And finally, I mean, it's not the very last point, but it's the last one we're going to do. log base 2 of 1/8 is equal to -3 because 2 to the -3 is equal to 1/8. So then if I want to graph this, so I've got my points 1, 2, 3, 4, 5, 6, 7, 8. I'm going to go 1, 2, 3, -1, -2, -3. So let's see. So I've got the point, let's start here with 1, 0, and then 2, 1, and then 4, 2, and then 8, 3. And I've also got the point 1/2, -1, 1/4, -2, 1/8, -3. So here's how this thing is looking. It's kind of hard to graph. Okay, so a couple things to see. Well, first of all, let's label these points just so we can really see them. This is the point 8, 3. This is the point 4, 2, 2, 1, 1, 0, 1/2, -1, 1/4, -2, and 1/8, -3. So some things to observe. First of all the x and y coordinates are interchanged, right? Here I have 3, 8, here I have 8, 3, 2, 4, 4, 2, 1, 2, 2, 1, etc., etc., etc. Also, all of the x and y features are interchanged. Let me just move this a tiny bit here. Sorry, 1 second. So, meaning here, the y-intercept is 0, 1. And here, instead of having the y-intercept of 0, 1, I interchange x and y, and I get an x-intercept of 1, 0. Over here, I have a horizontal asymptote of y equal to 0. Over here, I have a vertical asymptote of x equal to 0. We do get a vertical asymptote here because your x values can only get closer and closer to 0, but they can't ever be 0. So just like, in fact, we'll go to the next page for this, but I'm going to say, right, just like this function can never equal 0, this function, you can never take the log of 0, right? If you can't have, right, if we're interchanging all the x's and y's, if y can't be 0 here, that means x can't be 0 here. Also, let's say a few more things about this because it's kind of neat. So, yeah, let's skip this piece of paper here. Oh, wow, I'm really just bleeding right through. I'll use these for other things. Don't worry, they're not just going to go in the trash. So I will say what we really have here is what's true whenever you graph inverse functions, which is that they are symmetric about the line y equals x. So this is my exponential function, and this is my logarithmic function. Y equals 2 to the x, y equals log base 2 of x. These have, or these are, reflections of each other across the line y equals x. Whenever you reflect graphs across the line y equals x, and I'm flipping my hand back and forth like that's helpful. Whenever you have reflections across the line y equals x, the x and y intercept, the x and y coordinates all change. So right here, I'm getting 0, 1. Here, I'm getting 1, 0. And that kind of just goes right there. Here, I'm getting the point 1, 2. Here, I'm getting the point 2, 1. Here, I'm getting the point 2, 4. Here, I'm getting the point 4, 2. And so on and so on and so on. Yeah. So a few more things about logarithms before we start really just graphing them. And again, the way we're going to graph them is going to be very similar to how we graphed exponential functions yesterday, in that we're going to kind of do it doing the least amount of stuff we can. So let's do, yeah, I know it's a bunch of space here, but I'm going to go to the next page anyway. So in general, if you have y equal to log base b of x, well, first of all, just like with exponential functions, our bases should be greater than 0 and not equal to 1. We can't have a log, we can't have, right? If our base was 0, you'd have to be like 0 to what power equals x? That's not going to work, right? Because 0 to any power is 0. If your base was 1, that's also kind of a problem because you're saying 1 to what power is going to equal x, and 1 to any power is 1, so you're not going to get there. And the negative bases are weird. I will also point out, even though your bases can be anything, typically our bases are nice integer numbers. Like 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so on and so on. So I should really say positive integers, although I guess I already ruled out negative numbers because our base has to be positive. So like 2, 3, 4, 5, 6, and so on and so on and so on. The only exception to that is, of course, everyone's favorite base, and e, which is approximately 2.7. You can have other bases, right? Pi could be a base, 1/2 could be a base. Other weird numbers could be bases, square root of 2, 2/3, 7/5. But usually logarithms, the bases are, even though you can have any base, you really mostly just see nice integer bases. Usually, and e, of course. Usually you really just see base 10 and base e. But other bases are totally fine. So a few things to note about this logarithmic graph. So it looks like this generally. It has an intercept of 1, 0. I will point out that even though it kind of looks like it starts to kind of level off, it never actually flattens out. There is no horizontal asymptote. This graph keeps getting larger and larger and larger forever and ever and ever. So a few things to observe. The domain of this graph, of this function, I should say, for y equal to log base b of x, the domain is all positive numbers. The range is all real numbers. This goes as low as negative infinity. Well, I mean, it goes as low as you can without bound and as high as you can without bound. So the range is everything from negative infinity to infinity. We have a vertical asymptote at x equal to 0, and we have an x-intercept at 1, 0. I would also point out that all of these things are exactly the inverse things of the exponential function. So just as a real quick reminder, if you had an exponential function that looked like this, y equal to b to the x, this exponential function has a domain that is all real numbers. I'll remind you all, the domain is all the x things. So look, all the x things here is the same as all the y things there, which is the range. And the range of the exponential function is all positive numbers. So inverse functions have this kind of special quality that their domain and range are interchanged. If this is my function and this is its inverse, or vice versa, this is my function, this is its inverse, the domain here should equal the range here, and the range here should equal the domain there. Always true. And then my horizontal asymptote is y equals 0. My y-intercept is 0, 1. So all these things have interchanged their roles, which is kind of great. Yeah. Almost to the part where we actually talk about graphing the things. So yeah, if I'm going to graph some logarithmic functions, I'm going to do the least amount of work I can. And that's what I expect from you as well, to do the least amount of work you can kind of get away with when you're graphing a logarithmic function. And just like with exponential functions, if they're not shifted or transformed or reflected or anything like that, you can kind of get away without doing very much at all. For example, if I want to graph y equal to log base 3 of x, here is what I would expect to get. XY coordinate system. And the x-intercept of 1, 0, and then it should look like this. And I should label that point, or somehow indicate that I know it is 1, 0. If you really feel like that's just not enough, another point you could plug in would be setting x equal to the base. So, right, we get the point 1, 0 because log base 3 of 1 is equal to 0, right? 3 to the 0 is equal to 1. And if you want one more point, so this is right when x equals 1. I can also set x equal to 3. If I plug in 3, I get log base 3 of 3. And 3 raised to what power equals 3? Oh, 3 raised to the first power is equal to 3. So I could also plot the point 3, 1 if you really wanted to. Those don't look perfect. That's fine. If you wanted to be, and I don't need you to be, but if you really felt like you wanted to do a more detailed graph, you could do this. I'm going to go out to 9, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. That's probably too much. 1, 2, 3. So if you really want that, again, I'm good with you doing just this for log base 3 of x or log base whatever of x. But if you want to be a little more detailed, you're welcome to be. If I was going to plot some points, I'm going to pick x values that are nice powers of 3. So I'm going to pick like 3 to the first and 3 squared. I'm probably not going to actually do 3 to the third. But then also 3 to the 0th, 3 to the -1. I'm picking all powers of 3 for my inputs so that my outputs are nice. So now if my y value is log base 3 of x, let's start at the bottom. Log base 3 of 27 is 3 because 3 to the third equals 27. And log base 3 of 9 is 2 because 3 squared equals 9. Be careful again. I've seen lots of people over the years say that log base 3 of 9 is 3 because what they're thinking is 3 times 3 is 9. It's true that 3 times 3 is 9, but that means 3 squared is equal to 9, right? That number there, that number is the power. The power. Okay, so then log base 3 of 3 is 1 because 3 to the first equals 3. Log base 3 of 1 equals 0 because 3 to the 0 is 1. And log base 3 of 1/3 is -1 because 3 to the -1 is equal to 1/3. So then I could plot all these points. I'm not going to plot that one. Right? I didn't go all the way to 27. But I get the point 9, 2. So there's 9, 2. I have the point 3, 1. The point 1, 0. And the point 1/3, -1, which those ones always get a little dicey. So then looks like that. You don't need to do that much work for this graph. You're welcome to, but I only need you to do this. You can do this if you really want. If you've got all sorts of time on your hands and you really feel like, James, you know what? I want to draw a beautiful graph. That's totally up to you. I don't need you to do that. Okay, so let's look at a couple more examples and then we'll do some transformations. Also, you're welcome to pause the video if you look something right. Like you don't have to like watch it all the way through. In fact, now would be an excellent time for you to pause the video and try graphing y equals log base 5 of x. So pause the video. And now graph it. And now you can check to see how your graph compares to how my graph compares. So if I was going to graph, oops, come on. I want to graph y equal to log base 5 of x. You know what? My graph's going to look a lot like the one I just drew. I'm not trying to be perfect about it. Ooh, I'm really not trying to be perfect about it. So that's the point 1, 0. And if you really feel like you need another point, you'd be like, okay, that's the point 5, 1. I know those aren't to scale. That's okay. Doesn't need to be scale. I'm just trying to show the person I know what the graph is supposed to look like. And then you do have a vertical asymptote, right? This graph shouldn't cross over the y-axis, right? It should always stay on this side of the y-axis. So be careful about that. Yeah. If you really wanted one more point, you could go 1/5, -1 if you wanted one more. These are kind of like often when people graph like 3 points of an exponential or a logarithmic function, they often graph the intercept and then one nice point to the right and one nice point to the left. Or if it's, yeah. Okay, let's look at a few more examples. Oh, yeah. So just a quick aside, which is kind of funky. You can skip this part or ignore this part if it bothers you. Usually, like I said before, I'm always trying to scooch things around here. So usually for class U, usually logarithmic bases are nice, positive integers. Or E. But not 1. Right? You don't want log base 1. Why not 1? Well, if you had y equal to log base 1 of x, you can only calculate log base 1 of 1. Because, right, like if you tried to do like log base 1 of 5, you're asking 1 raised to what number equals 5? And that doesn't work. 1 to some power equals 5. Nope. So not going to work. So that's why 1 isn't a base. However, you can have bases like small fraction numbers. So for example, we don't usually do this, but you could have a base. We could have, for example, y equal to log base 1/2 of x. It's kind of weird because what you're saying here is 1/2 raised to the y power equals x. And this actually ends up flipping the graph over vertically. So again, this is not important. I'm not going to ask you about this. I mean, but I just want to make sure I'm covering all my bases. That's a good one, right? Covering all my bases to make sure that even though we don't usually have a base that is a number, really a fraction at all, but especially, less than 1, we could. And just like for exponential functions, when your base being less than 1 flips it horizontally, here your base being less than 1, since it's an inverse function, is going to flip it vertically. We could also plot some points. So it's good practice. I'm going to pick, again, nice powers of 1/2. Really, I'm speaking powers of 2, because a power of 1/2 is a power of 2. Power of 1/2 is a power of 2? Yeah, right? I know that 2 to the third equals 8. So 8 is a power of 2. I know that 1/2 to the negative third is equal to 8. So 8 is also a power of 1/2. Totally works. Okay, so here I'm just going to pick nice x values like I usually would, picking powers of 2, 8, 4, 2, 1, 1/2, 1/4, 1/8. And then I'm going to pick, or I'm going to find my y values, y equal to log base 1/2 of x. It's going to be kind of funky. Let's start at the bottom. Log base 1/2 of 1/8. So we're asking 1/2 raised to what power equals 1/8? Oh, that power is 3. I know that 1/2 to the third power is 1/8. And log base 1/2. If you want to skip this part, you can totally feel free to fast forward this part. This part is not that important. Or you can do the speedy thing. Where I'm like, yeah, okay. Right, I'm sure you all do that, right? Where you do like 1.5 times or 2 times, right? I certainly do it when I'm watching people's lectures. 1/2 squared is 1/4. Log base 1/2 of 1/2 is 1, because 1/2 to the 1 is 1/2. Log base anything of 1 is always 0, because 1/2 to the 0 is 1. Log base 1/2 of 2 is -1. 1/2 to the -1 power is positive 2. I shouldn't even say positive. I should say 1/2 to the -1 power is 2, because it's the reciprocal of 1/2. The signs of the numbers are not what's important here. Log base 1/2 of 4 is -2, because 1/2 raised to the -2 power is 4. And finally, log base 1/2 of 8 is -3, because 1/2 to the -3rd power is equal to 8. So look at these funky points I have. I have, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Oof. 1, 2, 3, 1, 2, okay, yeah. All right, so I plug in 8, I get -3. If I plug in, if I get x is 4 and y is -2, so 4, -2. 2, -1, 1, 0, 1/2, 1, 1/4, 2, 1/8, 3. So it looks like I've taken my logarithm of that graph and flipped it over vertically. So that's what's going to happen if you happen to have a base that is weird like that. Now, something that's kind of interesting about this is log base 1/2 of x is the same as negative log base 2 of x. Right? You can take your log base 2 of x function and put a minus sign out, which is going to flip it vertically. It's very, very similar to how, 2 to the negative, I should have started the other way. Sorry, fine. 2 to the negative x is equal to 1/2 to the x. I really should have started with this, said 1/2 to the x is the same as 2 to the negative x. Having your base being a reciprocal of an integer number ends up reflecting it horizontally. Whereas here, having your base being the reciprocal of an integer number reflects it vertically. Okay, if you want to forget all that, you can. It's not something I'm going to ask you about. So let's get on with the transformations of logarithms. Oh yeah. One one more thing, one more small thing. So something that does come up a lot is the following. So we see a lot of y equal to log base e of x, but we almost never write it that way. We abbreviate it because it's the most common base. It's the natural base. It's abbreviated as y equal to the natural log of x, or ln of x. I don't say ln of x because I used to have my office right next to a woman named Ellen, and I would say ln of x, and she'd be like, hey, James, what are you talking about? So I like to say natural log. You can say ln or natural log either way, or you can say ln. Ln, no, that's terrible. Don't say ln. Say natural log or say ln. But I really, 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 really have to emphasize, this is the same as that. It is just a different way of writing it. This is not special in any way, right? If you see this and you don't like it, just rewrite it with that. They are literally the same thing. In the same vein, the other base that comes up all the time is, of course, base 10, because we are a base 10 world in a lot of ways. So this gets abbreviated as y equal to just log of x without the base. So if you see a log with no base, they mean log base 10. And you can rewrite it like that if you want to. If you see ln of x, or natural log of x, it is really log base e of x. Yeah, a couple things to say here. So note, log of 1 is really just log base 10 of 1, and it's still 0. And log of 10 is really just log base 10 of 10, which is 1. Similarly, natural log of 1, which is just log base e of 1, is also 0. Log base anything of 1 is 0, because e to the 0 equals 1, because 10 to the 0 equals 1. And natural log of e is just log base e of e. And e to what power equals e? Oh, e to the first equals e. So there's just a few things to be aware of. Again, I really, really have to emphasize as hard as I can, that log base e of x is just an or I should say natural log of x is just an abbreviation of log base e of x. So don't let this throw you off when you see it later on. You'll see it a lot. It's a very common function. We see it all the time. This is just that. That's just that. It's just because mathematicians are lazy. One potential danger. Some math professors are assholes, and they decided that, so in upper division, high up math classes, for some dumb reason, people write the natural log of x as log. And they're trying to make things confusing. So there is one professor I'm aware of who sometimes teaches 21A. His name is Malassi, and he prefers to write the natural log as log. So if you run into that, just be aware that that's what's going on. So most of the time, natural log of x is log base e of x. Log of x is log base 10 of x. If someone says something different, you'll have to adjust for that class. Okay. So let's graph some things. So let's graph y equal to the natural log of x, which is just y equal to log base e of x. And I'm going to do the least amount of work I can. Okay, great. So here it is. Super special. Done. That's it. That's all I want. If you really, really, really insist, you can say, James, I feel like I need to graph one more point. So I'm going to plug in the nice base value for x, which is e. And log base e of e is 1. So some points that we plotted, x and y equal to natural log of x. We plugged in 1, natural log of 1 is 0. We plugged in e, natural log of e is log base e of e, which is 1. You don't have to make this table. All you have to do is draw this thing for me. Okay, so now we're going to do some shifting. Refreshing. Okay. Yeah. And while we could shift up and down, it's not very interesting. We're really mostly going to focus on shifting left and right. That piece of paper is dirty. It's kind of gross. Okay, let's just put that in the recycling. All right. So let's look at something like y equal to log base 5 of x minus 3. And of course, yes, we're graphing it. I should say we're graphing it. Graph. So the x minus 3 is going to shift this graph 3 to the right. Shifts the original graph 3 to the right. You can see that by knowing we have an x minus 3, and there's a couple ways to kind of think about how this works. One way is to think about where the vertical asymptote is. So the way I kind of like to visualize this is we have a vertical asymptote usually at x equals 0 because you can't take a log of 0. Now, I know you also can't take a log of a negative number, but 0 is kind of like the first place where you can't take the logarithm. So here, you could ask yourself, well, what value of x makes the insides equal to 0? So we could say, what value of x makes the argument of the logarithm, also called the inside of the logarithm, the argument, which is just what you're taking the log of, right? The insides, the guts of the logarithm. What makes the argument equal to 0? Well, if I set the insides equal to 0, I just get x equal to 3. And that's actually where our vertical asymptote is going to be. So the new vertical asymptote is going to be x equal to 3, which means I've shifted my vertical asymptote that was x equal to 0, 1, 2, 3 to the right. So we could think about, and let's think about graphing it that way. So here's my original graph. Here's my unshifted graph in red. Let's graph in red y equal to log base 5 of just x. It's going to look like this. I could plot some points, 1, 0, and the next point I would plot would be 5, 1. If x is 5, log is 5, 5. Okay. And then if I'm going to shift this 3 to the right, shift 3 to the right, here's what my new graph is going to look like. So I'm firstly going to graph my new horizontal, vertical asymptote. Jeez, I keep saying the wrong thing. So here's my new vertical asymptote at x equals 3. And then my new x-intercept is going to be, instead of 1, 0, it's going to be 4, 0, because I'm just adding 3 to that point. So there's my new x-intercept. And it's going to look like that. It's going to look the same as that, just moved 3 to the right. If you wanted to, instead of plotting the point 5, 1, you could plot the point. It does not look like it's to scale. That's okay. I'm going to plot the point 8, 1. Because if I plug in 8, I should write my graph name, right? Log base 5 of x minus 3. Or if I plug in 4 minus 3 is 1, and log base 5 of 1 is 0. In fact, let's write this down. It's good to write down. X, Y. If I plug in 4, log base 5 of 4 minus 3 is log base 5 of 1, which is 0, because 5 to the 0 equals 1. And if I plug in 8, log base 5 of 8 minus 3 is log base 5 of 5, which is 1, because 5 to the 1 equals 5. So that's what's happening here. We're shifting 3 to the right, and everything gets shifted 3 to the right. The vertical asymptote gets shifted 3 to the right. The x-intercept gets shifted 3 to the right, and the other point we happen to draw gets shifted 3 to the right. Okay, here's where I'd be like, I'm gonna ask for questions now. No questions. I mean, I know that you guys are a captive audience. So what I would encourage all of you to do next is, on your own, before I graph it, I want you all to try graphing y equal to log of x minus 2. So pause the video, graph it. You know what's interesting about this graph? Like other graphs, it doesn't really matter what the base is. I mean, it matters for extra points, but like the shape of the graph, shape's always the same. Oh, by the way, what is the base here? Oh, the base is 10. Right, so you could write this as y equal to log base 10 of x minus 2. Okay, pause it, graph it. I should say graph it, pause it, whatever. Do the thing. All right, now that you've done the thing, take a look. So here's how this is going to look. I'm just going to take my usual graph, and I'm going to shift it 2 to the right. In fact, I'm really going to think about the fact that my vertical asymptote I'm going to get by setting the insides equal to 0. That's my vertical asymptote, which is what I would get by shifting this thing 2 to the right. There's my new vertical asymptote. My new x-intercept is going to be just one more than that, because the x-intercept, unless you've done some weird kind of stretching, the x-intercept is usually just one away from your vertical asymptote. I will also point out, we could find the x-intercept the long way. What do I mean by the long way? Well, how do we usually find the x-intercept? Oh, we set y equal to 0. So we could say x-intercept. So I'm going to set y equal to 0. So taking my equation here, I'm going to say 0 equals log base 10 of x minus 2. But I know that 0 is the exponent. So I can rewrite this as, oh, what's my base? That's why I'm saying base this whole time. Log base 10. I do really recommend when you're reading a logarithm, you say the base in your head or out loud. Say log base 10 of x minus 2. Don't say log 10, say log base 10 of whatever is in the argument. So that base raised to that power equals what's in the argument. But 10 to the 0 is 1. And if I add 2 to both sides, 1 plus 2 is 3. So there's my x-intercept, just like we knew it was. Right there. And then we graph it in the usual way. It's got the usual logarithmic shape. This one would probably look less steep, or I mean, like it would look flatter, because really the next, right, if I was gonna plug in the next point I would need to plug in x equal to 12, because 12 minus 2 is 10, and log base 10 of 10 is 1. So I know I would also get the point, if x is 12, y would be log base 10 of 12 minus 2, which is log base 10 of 10, which is 1, because 10 to the 1 equals 10. So way over here would be the point 12, comma 1. But you don't have to find that point if you don't want to. Okay. Shifting to the right is not too terrible because we don't get any y-intercepts. Shifting to the left, on the other hand, does introduce the possibility of y-intercepts. So let's do that. I really just realized, like, I hope I'm recording. I am recording. Okay. I was worried for a second. I was like, it's a lot of talking to not recorded. Okay, so let us look at this example. Y equal to log base 3 of x plus 9. And of course, we're going to graph it. So if I'm graphing a logarithm, I'm usually thinking about where is my vertical asymptote. Vertical asymptote, we're just going to get by setting the argument equal to 0. So x plus 9 equal to 0. You get x equal to negative 9. So my vertical asymptote is 9 to the left of where it would be. So this does, in fact, as I had already kind of mentioned, this shifts the graph 9 units to the left. To the left, to the left, to the right, to the right, to the right. Okay, yeah. I know, I have no audience. I'm just going wild. Okay. So, yeah, let's graph it. Sure, let's do it over here. Oops, I want, yeah. Let's see, so I don't really want to be that precise. So I'm just going to say, here's my vertical asymptote over here. Now you should ask yourself, doing the least amount of work possible, if my vertical asymptote is x equals negative 9, what should my x-intercept be? Well, take a minute, pause it, think about it. Okay, I assume you thought about it and have gotten an answer for yourself. If my x-intercept normally would have been positive 1, and I moved everything 9 to the left, 1 minus 9 is going to give me a negative 8. So that's where my x-intercept should be, is at negative 8. It's going to look like this. Ooh, I went kind of low there. Let's. Okay, we got this. Sure. Just going up and up and up forever and ever and ever, right? Doesn't level off, right? This doesn't level off. It just keeps going up. It just goes up really, really slowly. So that point there is negative 8, comma 0. Again, you could have, if you didn't know that it was just going to be, if you didn't know it was 1 minus 9, or that it's always 1 away from your vertical asymptote, you could have done the thing where we're going to say, well, I'm going to find my x-intercept by setting y equal to 0. That totally works. So then 0 equals log base 3 of x plus 9. We rewrite our logarithmic equation as an exponential equation. My base is 3. My power is 0. It's equal to x plus 9. But 3 to the 0 is 1. 1 equals x plus 9. And then subtract 9. And 1 minus 9 is -8. So that's my x-intercept, -8, 0. I will also point out that this graph, this logarithmic graph that is shifted to the left, has a y-intercept, and we should definitely find it. So to find the y-intercept, we're going to do the usual thing. We're going to set x equal to 0. So if I set x equal to 0, I'm going to get y equal to log base 3 of 0 plus 9. When I say set something equal to 0, I'm just saying take your equation, your thing you're graphing, and just replace the y part with 0 if you're finding the x-intercept, or the x part with 0 if you're finding the y-intercept. That's all I really mean when I say set something equal to 0. So then I have y equal to log base 3 of 9. But log base 3 of 9 is, it's not 3, it's 2, because 3 squared equals 9. So my y-intercept is the point 0, 2. Because if x is 0, y is 2. Yeah. All right. I guess I could write there. So you all should try this next one on your own, completely. So I want everybody, before you watch me do it, I'm going to do it. You should try graphing with all of the details, y equal to log base 8 of x plus 4. So I want you to find the vertical asymptote, the x-intercept, and the y-intercept in whatever way works best for you, right? You can just be like, oh, I know the vertical asymptote and the x-intercept are just shifted, so however much to the left, to the right, but you have to do a little bit of work to find the y-intercept. So pause it, do it. Now that you've paused it and done it, come back and see what the whole thing looks like. So we are taking, in fact, just as a reminder, here is our parent graph. So the parent graph, ooh, sounds like the parent trap, the parent trap, the parent graph, parent trap. Parent trap wasn't all right, maybe the original. Okay. I mean, the other one with Lindsay Lohan's also pretty good, I guess. So here's my parent graph. Got the point 1, 0 here. And if you really wanted, I could also have the point, 8, 1. Right? The parent graph is, I should say, is y equal to log base 8 of x. And then we're taking that graph and we're shifting it forward to the left. And the way I really know it's for the left, like I know when you add inside, you shift forward to the left. It's because x needs to be 4 less than it was to get the same kind of input, right? If I was graphing this, if I plug in x equals 1, I get log base 8 of 1, which is 0. Here, x has to be 4 less than that to get the same result. So if x is, let's see, 1 minus 4 is -3. If I plug in -3 plus 4 is 1, and then log base 8 of 1 is 0. So that's kind of the idea. X has to adjust so that I get the same outputs I got before. Or you can find the vertical asymptote by saying x plus 4 has to equal 0, so x equals -4. So we know we're shifting 4 to the left. Okay, so let's start graphing things. I'm going to be a little more precise just to make my graph look nice. I know I don't need you to be super precise. I just figure like maybe once in a while I could be kind of precise. Okay. So then I know my x-intercept is going to be -3. You could also do the work to find it if you wanted to, right? If y equals 0, then 0 equals log base 8 of x plus 4. That becomes 8 to the 0 equals x plus 4. Well, that's 1 equals x plus 4. 1 minus 4 equals x. So x equals -3. Or you just be like, James, I know I'm taking my point that was 1, 0 and shifting it 4 to the left, so I'm getting -3. And then I like to graph it first before I find the y-intercept. I know I'm going to have one. Oops, that's kind of really close there. Again, right, your graph shouldn't cross the vertical asymptote. It's just the first, right, it's going down, 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 down forever, and it's getting closer and closer and closer and closer and closer and closer to x equals -4, but never actually getting to touch it. Super duper close, but not quite there. So the y-intercept, we have one. There it is. Let's find out its value. So we're going to set x equal to 0. And we're going to get y equal to log base 8 of 0 plus 4. So y equals log base 8 of 4. You might know what that is. I don't off the top of my head. So I'm going to rewrite it as an exponential, right? The other one, like log base 3 of 9, super straightforward. 3 squared is 9. You also could have solved that previous one. Let me drop it here real quick. Right? If you wanted to, right, you could have been like, oh, instead of, oh, that's not the thing, right? Where'd you go? Yeah, I got papers all over the place. Sorry. Instead of doing, right, instead of just saying it's 2, you could have been like, well, I know that 3 to the y equals 9, and then 3 to the y equals 3 squared, so y has to be 2. That's the other way you could have found what the y was equal to. For this one, it's a little harder, right? 8 to what power equals 4? It's not 1/2. 8 times 1/2 equals 4. 8 to the 1/2 is the square root of 8, which is like 2 root 2, which is 2.8, which is not what we're looking for, right? I don't want what I multiply by 8 to get 4. I want what I raise 8 to a power as a power. I want 8 to some power equals 4. So 8 raised to the y power equals 4. And here's where we get to do the tricky thing where we say, oh, 8 and 4 are both powers of the same number. They're both powers of 2. So 8 is 2 cubed. And then it's 8 to the y, so it's 2 cubed to the y equals 4. I'll try to make sure my y's and my 4's look different. And then 2, well, I'll just do it in the next step. 4, I should have written as 2 squared. So then in the next step, we have 2 to the 3y equals 2 squared. And then when equations are equal to each other and they have the same base, we get to say that the powers are equal to each other. So we really get to say, oh, that means 3y equals 2, which means that y equals 2/3. So this point here is 0, 2/3. This point here is -3, 0. This is x equal to -4. And that is about it. Yeah, there are certainly lots of other things to say about logarithms. There's some rules for adding, subtracting logarithms, that kind of stuff. We're not going to get into that, but definitely, if you have questions about logarithms, you're welcome to ask me. I hope this was understandable. If you want more, I should just honestly, so if you want more examples, there are other videos of me on Canvas talking about logarithms. Also, Khan Academy. I guess I could have mentioned that at the beginning of this. I imagine most people are familiar with Khan Academy at this point. Khan Academy is a good resource. You can certainly look there. So yeah, I hope you all have a lovely last week of STEP that is relatively low stress. Certainly, I would encourage you all to try and get this final out of the way as soon as you can. That way you can focus on other things. Yeah, I really look forward to seeing you all in the fall. Please do, even if you're not taking a co-class or a pre-16 with me, come see me. I'm happy to talk about math. I will definitely figure out and post when and where my office hours are going to be for the fall so that you can find me and get help with math, whatever way, shape, or form. It's been a pleasure getting to know all of you. I really, really enjoyed teaching you all in STEP this summer. You were all a lot of fun, and I really liked getting to know you all. So take care. I'll send you some, I'll post some pictures in Canvas from Hawaii so you can all see me and my wife and my mother-in-law having a lovely time and the lovely views and all that kind of stuff. And yeah. All right. That's all I got. Take care. And I look forward to seeing you on fall quarter. Bye. Nope, that's not bye now. Okay.